artificial intelligence took a really huge leap in terms of quality in the last few years, mostly because of neural networks. Um, Neural networks, for our purposes, these are enabling technologies. So um, this little outline that I put here kind of describes where they fit into our in as part of artificial intelligence. So artificial intelligence is a more general term for, as we talked about, just the ability for computers to do things that are apparently intelligent. And machine learning is where we start with some data, some previous data, and we ask the computer to learn how to combine features of the data to make predictions. And underneath machine learning are neural networks and deep learning, where deep learning is really just neural networks on steroids. So we have to kind of figure out what these neural networks are. Now, as I said, these were a big contributor. There were certain tasks such as classifying objects from images, which were attempted for a long time, but it wasn't until the use of convolutional neural networks that it actually started being accurate enough to be put into commercial practice. So you can see the practical use in computer vision of object recognition for surveillance cameras or autonomous vehicles. Another kind of neural networks, which is called recurrent neural networks, are good for sequence data, but we're going to get into that in another video. But suffice it to say that the reason why we have, all of these virtual assistants that we can talk to is because voice recognition has gotten really good because of neural networks. And basically, classification of natural language expressions has become really good now because of neural networks. So a lot of the tasks that were, the tasks themselves are not new. What has happened recently because of neural networks is that the accuracy has gotten so good that these are now a valid addition to artificial intelligence, and it's a huge leap forward. But I want to introduce the technical side of this by talking in a more concrete way about what these are and kind of relating them to some of the analytical tasks you already know how to do. I don't want to immediately start talking about the spooky similarities with brains and how they work. I don't want to get into that, at least not very much. I want to talk about something more specific, like that you might actually be doing. Let's start off by looking at predictive modeling. So let's just take a very concrete case where we want to do something, not too fancy and not too complicated. All we want to do is be able to predict what a house's price would be. What should the predicted price be given the number of square feet and the number of bedrooms? Okay, so this is a predictive model, and what we would typically do for something like this is we would just do a linear regression, where the regression would supply us with some weights that we can multiply by the square feet and bedrooms and combine them into some kind of model for what the price would be. So we might have some historical data like this, where I've got just going on what has happened in the past. I've got here's the price in this column. This is the number of square feet and the bedrooms. And I want to do a regression where I predict the house price based on these two variables. Okay, so I'm going to do this in SAS Jump, which you have access to as a student here. So this is my, okay, so this is Jump. I've got this, that's the general Jump window. And here is this data pulled into Jump. Okay, so there again, it's the same data, just now it's pulled into Jump, which I like to use for regression. So okay, I'm going to make my predictive model now. I just do analyze fit model, and I'm going to predict the house price, so that's my Y variable, based on the square feet and bedrooms. And so this is where you put your dependent variable, and this is where you put your independent variables, and we'll just leave the rest of this as default, and we'll run it, okay? And don't worry about a lot of this. This is about model evaluation and so forth. So I'm just going to show you kind of the point of getting these things is to, we want to make predictions with this. And I can see that I've got, an R-square of 92% and adjusted R-square to 90%. So these two variables help us quite a bit in predicting. But these are what I'm interested in. These are the parameter estimates down here. And these supply me with these actual numbers that I want to use for my predictive model. So I'm going to come back over here. Okay, so now that I have these weights, I'm just going to put in some placeholders here for 0. So looking down here, I see I have an intercept. Let me just write that down. So that's 103.955, 103.955. Okay, and then what this is telling me is that I should multiply the number of square feet by 0.016, and don't worry about that insignificant p-value right there, 0.016, so I'm going to multiply by 0.016 for square feet, and I'm going to multiply bedrooms by 62.117, 62.117. Okay, so my predicted price is going to be it's going to be this intercept plus square feet times the weight of square feet plus bedrooms times the weight of bedrooms. Okay, so it's just a weighted sum. And that is now my predictive model. So I can say, okay, if I've got 1,200 square feet and 2 bedrooms, okay, I can expect to pay $247,000. If I add one more bedroom, okay, it's just gone up. If I get a lot more square footage, whoops, that's a lot less, a lot more square footage, it goes up accordingly. Okay, so what we have here is a predictive model. Okay, it's just a predictive model based on a weighted sum. Okay, so very simple sort of thing that you do. Okay, so another slightly more complicated model would be to predict a probability. And I went over this case in a previous video, but we can do a similar thing where we have slightly different data. So this is the churn data. So this is the the historical record of churn, where churn, each row here is a customer, and the churn code is whether the customer has canceled our service. So this is historical data that lists the number of calls that this customer has made and the number of years they were with the company, and then whether or not they left. So we can now use this to build a predictive model of estimating, what is the probability that somebody is going to churn. And for this, we use what's called a logistic regression. So again, we do the analyze fit model, and I'm going to predict the churn code based on calls and years. And I'm going to try to predict 1, and it's going to be a nominal logistic regression here. Okay, so once again, what I have here, down here under parameter estimates, so these are the numbers that I'm going to put into this model that I'm interested in. Okay, so what this is telling me is that, again, just like up here, I'm going to have an intercept. Okay, and I'm going to put the, I'll just put the intercept here. No, I should put the intercept here. So the intercept is 2.871, 2.871, and once again, I'll put in just some placeholders here. I'm going to multiply calls by 0.075, and I'm going to multiply years by negative 0.845. Negative 0.845. Okay. Now, in this case, this weighted sum So let's just put in some slightly more real data. So let's say 20 calls and 5 years. Okay, now this case I'm going to do a weighted sum just like up here with this model. So it's just going to be this intercept plus, the calls times the weight of the calls plus the years times the weight of the years. Okay, now in this case, this weighted sum gives me something called log odds, and that's just how logistic regression works. What it's actually giving you, the linear prediction is actually giving you log odds. But we can convert this to a probability by applying a function. So I'm just going to apply a function just to make it something slightly more usable and interpretable, which is probability. And we just do that. And don't worry about why this is. This is just how logistic regression works. You convert this with the probability by doing this function. Okay, so now I have this probability, so 50-50. However, if their number of calls goes up, it now goes up to 71%. If their number of years with the company is 2, now it goes up to a full 97%. Okay, so now I've been able to build a predictive model of the probability that a customer is going to leave based on these calls and years. But in this case, I did not only a weighted sum, but I had to apply a function. Okay, so let me go ahead and write this, write down what we've done so far, what we've modeled. And so in the first case, so when we were predicting the house price, we had this sort of situation where we were predicting a Y based on, we had some intercept plus some weight times the first variable, which was the number of square feet, and then plus another weight times the other variable, which is number of bedrooms. Okay, so the central problem in estimation then was finding out these weights. We need to know, okay, what is this, and what is this? So we take our historical data, we have y, x1, and x2, and it figures out what these are. In this case, it's just ordinary least squares regression, so it was able to find those pretty easily. Now, okay, so in the other case, so the next case, we were trying to predict the probability. In this case, we wound up, we had a similar thing where we had an intercept, and we had a weight times the first variable, and a weight times the second variable. Okay, so again, we got these weights. But this time we applied some function. I'm just going to do that. So we applied some function to that linear prediction. But again, so we had weights this time. So this is just a, we'll say this is just a weighted sum. And this was some function applied to a weighted sum. Okay, I'm sorry for the sloppiness. It's hard to write with this. Okay, so, and this is an F. Okay, so one way we might rewrite this. So let's take this first one then. I'm gonna draw a line here. So how might we can redraw this to kind of have a little bit of a geometric interpretation. So let's say what we're going to do is we have our input variables, that x1 and that x2, and then this will just be for my intercept. And I'm going to draw these as little little nodes on a network. Okay, so what we're doing for this first one is we're taking these input variables and we are producing an output by applying a weighted sum. So this was this weight down here. This was this weight. and this was, oh, whoops, sorry, this should be 1, and this is 2. Okay, so this is one way of visualizing what we're actually doing here. Is we've got these inputs and we want to produce a certain output, and what we need to know are these weights. So the process of linear regression is just one of finding these weights. Okay, now in the case of this other one, it was only just slightly different. Once again, we had these two input variables, and we were combining them with a weighted sum as before. That's 2 and beta 1. But this time we were applying a function to that weighted sum and then arriving at an output. Okay, so this is just a different way of visualizing what we're doing, but ultimately what we're doing is we're starting with data and we're using some learning process to arrive at these weights. Okay, in this case, the weights are slightly harder to learn because whatever algorithm is learning the weights has to take into consideration this function's transformation. So, but eventually, the problem is one of coming up with these weights. Okay, now let's take a look at how that logistic regression did, just for fun here. So I see, okay, so we had an R square of 0.49. So, that's pretty good. That means that it'll be, it accounts for, about half of the variance. And we've got these fit measures here with a root mean square error of 0.344. So it's not perfect, but this is kind of where data science stopped for a while, and they just said, well, this is combining the data in this way gives us as close as we can really get of a prediction. But then somebody quite clever said, well, okay, is it really necessary to only have one step like this? Couldn't we do something like this? What if we did this instead of just doing that one step? What if we took our input and then instead of just going straight to the output, what if we had just put a bunch of outputs here? So we combine the data to okay, and then maybe and then went to our output. Okay, all right, so this is fully connected. I don't think I got them all, but okay, there we go. So now what it's doing is it's saying, okay, we need to do some kind of weighted sum. So each of these is going to include a weighted sum, and it's going to also apply some kind of function, just like that with logistic regression. Okay, and so that would mean that when we're training this thing, we have all the data. We have our x1, our x2, and we have what the output should be right here. And now what the training algorithm has to do, so ultimately the goal is to have just this step-by-step way of doing weighted sums and then applying some function. And so we do it on this level, then we do it on this level, we do it on this level, and then this last step is going to give us an output. Okay, so it's basically multiple different regressions and with different functions. And so what they found out was that this was astonishingly accurate. That instead of having, like, for example, we had a root mean squared error of like 0.34, just going with the one level, like this, is that if you have something like this, you're down, you might go down by a huge factor. Like all of a sudden your error rate is only like that. So when you have a something like this where you can put in your data and get the right output, you have just an unbelievable amount of accuracy on your training and holdout data. But the key challenge here is, remember that when we were making this, we had to learn 3 weights, right? So it just said, okay, we've got this input and this output, find the right weights that will get us from this input to this output. Now, the course of training this thing means, okay, we have these 2 inputs and this output. Now we have to find weights for all of these, so I'm not going to count them all, but that's 1 and that's 1, and there's just a bunch here. And so we have to work backward, given the output and this input, and then tweak all of these different weights. So the first, back in the 80s, when they first conceived of these things, they started off by putting in random weights and then just kind of tweaking them as they went, just looped through and tweaked them, like maybe increase this one a little bit, decrease this one, increase this one, and until they just kept adjusting it until it worked. And this took just way too long. And so consequently, research, using these, and this is a neural network doing a predictive model with a neural network like this was stalled because there was just no efficient way to get all of these different weights. It just took too long, and the increase in accuracy that you got was just not worth the trouble. But eventually, certain things fell into place. I have a slightly nicer picture here to just also show what I'm talking about here. So again, here are the inputs. These are the weights. So these are all the variables, and then you combine these in a weighted sum, and then you apply some kind of function. So you've got all these inputs that are combined to make some kind of output, and they call this an artificial neuron or a perceptron. And this, the reason why these are called neural networks is because these bear some superficial similarity to neurons. The actual neurons in your central nervous system work the same way, where you have all of these different inputs that go into the neuron. You've got some processing, and then it has any number of outputs. But then the processing part of this is, what kind of function goes on in here to determine what these outputs are. Okay, so this is why they're called neural networks, because these weighted sum things that when you hook them up together actually look, they have some kind of physical resemblance to these neurons, because these outputs will go into another neuron, and so what you wind up with is multiple layers of actual neurons, just like what goes on here with these artificial neurons. Okay, but the big holdup here, though, was, as I said, coming up with an efficient way to determine these weights. And let's see, I have it here. Okay, especially when you start doing craziness like this. Okay, so these are the inputs. So this is always the input layer. And these are the outputs. Now we've always we've always had one output layer, but you could have an output which has several different values, like let's say 1 2 3 4 5 6 7 8 9 10 11 12. You have, let's say this is a classification task, and you have 12 different classes, and your output is going to be a probability of each class. So this is probability 0.1 there, 0.02 there, and then maybe down here you've got like 0.9. Well, it can't be 0.9, but like 0.6. Then you could say, okay, well, now I know that this is the most likely class. So you can have multiple outputs. But when you have a lot of inputs, and then you have these things in here, which are just kind of like where you store the weighted sums, these are called hidden layers. And so we've got 1, 2, 3 different hidden layers here. And well, how many hidden layers do you have? Well, we're going to get into that in a minute, but so you can see that once you start adding these up, there are enormous numbers of weights to figure out. So you've got all your input data, you've got your historical data, and you're trying to learn all of these different weights. It just became an intractable problem. So progress was stalled until a few things happened recently. One was that data became available. Okay, we have large data sets that make it possible to train a network like this. As you can see, with this number of weights that have to be estimated, unless you have a lot of rows, you're going to run into degrees of freedom problem. The other thing that happened is improvements in software algorithms, particularly backpropagation. So what backpropagation was a more efficient way of actually finding the weights. So instead of just initializing all of these to a certain arbitrary, just a random number, and then tweaking them up and down, backpropagation became a little bit more sensible and efficient. We're not going to get into it because it's way too complicated, but it made it possible to actually come up with these hundreds or thousands or even millions of weights. Okay. The other thing that happened is that hardware became available that can efficiently process these. Now, this GPU stands for Graphics Processing Unit. Now, why graphics processing unit? There's no graphics involved here. Well, all of these operations here are weighted sums, which means you have something like this. You have let's see, you can have x1, x2, any number of variables that you're going to be multiplying by weights, weight 1, weight 2, ... weight n. And so what these operations are, these are linear algebra. And it turns out that there was a lot of linear algebra involved in generating computer graphics. And so over time, the folks at NVIDIA came up with specialized hardware specifically for doing linear algebra. And so, with a computer screen, you've got, thousands of pixels, right? Each little pixel has to have color values calculated for it. And so there are these millions of matrix multiplications, matrix and vector multiplications involved for every single pixel. And so the graphics processing units got very good at doing these kinds of linear algebra operations and parallelizing them so that they could calculate all the different picture elements simultaneously. So it turns out that these graphics processing units, of which I have one on this machine right here, and I'm going to show you a neural network implementation in a minute. These also sped things up tremendously, so that instead of spending days trying to find all these weights, the combination of the software back propagation in the GPU made it possible to find the weights in a reasonable amount of time. Okay, so so when we have a lot of choices to make then. We have our inputs and we have our outputs, which are kind of given, but we can decide how many layers, and we can decide how many of these, and how do we go about it? So here are the decisions that we have to have. So in this little neural network here makes it a little bit simpler to look at, because there's only one hidden layer here. One hidden layer. And we've got three inputs. They're doing their weighted combination, their function application, and combining their outputs, combining those into these outputs here. So in this kind of demonstrates, okay, well, how did they decide to have just one hidden layer? So the first decision we have to make is how many hidden layers should you do? And then secondly, how many units on each layer? So this one just, got a bunch on this layer and then, only had 5 here, and, fewer here. How in the world did they come up with that decision? So we have to decide, well, how many units on each layer? And then remember, so each one of these, you take the weighted sums and then you pass them through that output, right? Whatever. So this function, there are any number of functions that you could do. Okay, they're linear functions and stepwise functions. So you have to decide on which, after you take that weighted sum, what function do you apply at each unit? Okay, and then finally, this is a much more loaded question I'm going to get into in a minute. So I want to show you how you can make a neural network quite simply using JUMP. In another video, I'm going to show it to you in Python, but for now, let's just take this churn data that we have and let's just make a neural network. So instead of just doing the one step, where is it? Instead of just doing the one step logistic prediction here, we're going to actually have a hidden layer or two. Okay, so I'll come here. Okay, this is just the same old data, calls, years, churn, and I'm going to go to Analyze, and sorry, not Fit Model, Analyze, Predictive Modeling, and Neural. Okay, so SAS/JUMP provides you with a point-and-click way to make a neural network. So I'm going to predict my churn code. So this interface, this dialog is very similar here. And I'm going to put in my X factors right here. Okay. All right. So now here is where I can make those choices that I was just talking about. So in the case of SAS, this tool that they give you, they kind of choose for you that you can have up to 2 hidden layers. Okay. Now theoretically, you can have 3, 4, 100, 1,000 different hidden layers, but for this tool, we have a maximum of 2 hidden layers. Well, let's go ahead and use. Let's go ahead and just have one hidden layer for this first one. Now, so what this is saying is you had, for the first hidden layer and the second hidden layer, you can pick the function that you want to apply on, for the number of nodes to apply that function to. So I'm just going to, the default setting is on the first hidden layer, apply this function, which is the hyperbolic tangent function. Don't worry about that. It's kind of an S-shaped thing. And I'm just going to take all the default elements here. Okay, so let's not worry about reading this just yet, but let's take a look at the diagram. Okay, so this has now, okay, it takes the calls and the years and then passes them into 3 nodes on a hidden layer and then goes to the churn code. Okay, so the diagram before was just calls and years into churn code. Now it's applying functions on 3 units on a hidden layer. Okay, and now if I look up here, I notice that I now have a generalized R-square of 0.87. Remember, the R-square on the logistic regression was only I think 0.5 something, right? And then look at the accuracy. If you look at these confusion matrices, it actually does quite a good job of predicting. It was only wrong one time in the unseen code, the unseen data. Okay, well, let's take a look at another. Let's see if we can add more layers to make it even more impressive. So let's have a second layer now. Let's apply. Let's have two nodes, 2 units that do hyperbolic tangent, 3 that do linear, and then on this level, let's have 8 that do the hyperbolic tangent. So let's go ahead and generate that. So this is the new one down here. So I'm going to show the diagram of this one. Okay, so now we've got 1, 2, 3, 4, 5 units in this layer. 1, 2, 3, 4, 5, 6, 7, 8 in this. So these 8 are doing, see that S shape? That's the hyperbolic tangent function. And these 3 are the linear, and these 3 and these 2 are the hyperbolic tangent again. So it's going through 2 hidden layers before it goes to that churn code. Now let's see if we've gotten any better over here. Slightly different confusion matrix. It doesn't look like we gained a whole lot by this. You know, we can just keep trying and try. You know, we can just get, we can try to get funny about it. Let's see if we can break it. If we make 20 and let's say 12, let's see what it does. Okay, and let's take this diagram. Okay, yikes. And now let's see, we're actually less accurate now. Okay, so we might want to just stick with this one up here. How do we do 0.87, 0.85, 0.82? So we actually got worse by adding more layers. There's not really any theoretical basis for choosing the number of layers or the number of units per layer. When we talk about convolutional neural networks, we'll get into some of the more mind-blowing aspects of that. But for now, we just say we'll try through trial and error. We've determined that this is our best neural network. And so if we want to deploy this, we would do something like, let's see, publish the prediction formula. And then we could just do something like, okay, well, you save it as some Python. Okay, so now we have our functions. And you can see in there it is. It's got the 3 different layers where it's applying the hyperbolic tangent function to the data that you have in there. Okay, so you can push it out to Python. Okay. All right. So this is this is kind of the entry point for doing neural networks. Again, they come back to this idea of you want to make a prediction. You want to make some kind of prediction, and you do it by combining a weighted sum with some function. And all that we're doing with these more complicated setups is we're doing those weighted sums and combining them with functions on multiple layers. And it turns out that these provide more accurate predictions. Now, the last question that I have here is, should we make a fully connected network? So in this case, everything we've done so far, we've had a weight that is an arc going from every single node to every single other node. But what if we just want to say, have this one going to these 2, and then this one going to maybe those 2, and then this one just going to that one, and maybe that one up there? How do we know? How do we know, first of all, whether dense is going to be better than kind of a selective graph? Or if so, if it is better to select, and not have everything connected, how do we learn which ones we should connect to which? So this is where we get into, as I said, one of the more mind-blowing aspects of neural networks, and that's convolutional neural networks. So with convolutional neural networks, these actually, or CNNs or convnets, these actually learn the network connection, how it should be connected. So you just say, okay, I have this number of layers and I have this number of units, and then it goes and learns which ones it should connect. And it does this by noticing patterns. So for example, if we have an input image, and convolutional neural networks tend to go along with images, for some reason, this just seems to be how vision works. And in fact, I understand that psychologists have found that the visual cortex is structured much like these convolutional neural networks, where we have some input. So the actual input consists of all of these pieces, and the convolutional neural network will actually divide them up into components on this layer, where it'll say, well, this layer is well predicted by these 4 things, and this node is predicted by just these 2, and this one is predicted by these 5. Okay, and so it combines certain pieces of the input into certain nodes here on this layer, and then from those it gives output, which in this case is it predicts it's a cat. So on this layer, it just pulls in the input. This is the input layer here. And this here, it's identifying an eye. Here, it's identifying a nose. And here, it's identifying, I think that's an ear. Yeah, it's an ear. Okay, so when you use a convolutional neural network, you're actually going to breaking down the image into individual pieces, okay? But you do so, again, with weighted combinations, okay? In my next video, I'm going to show you a neural network that's used for kind of an interesting challenge, which is recognizing handwriting. I've got the MNIST data collection, which is 60,000 handwritten images. And so how would you train a computer to identify 3? Well, we're going to use a neural network, and I'll show you that next time.